and welcome to today's webinar. On behalf of New Food and XENON, I'd like to thank you all for attending. I'm your moderator, Bethan Grills, editor of New Food. Today's speakers will be Lou Panico, CEO at XENON Corporation, Dr. Saad Ahmed, Vice President of Operations at XENON Corporation, and Beining Ouyang, microbiologist at XENON Corporation. Following their presentations, we will move on to a live question and answer session where you can pose questions to today's speakers. You can submit questions at any point during the webinar using the questions panel situated in the menu on the right. I will now pass over to today's keynote speakers.
Thank you. As noted earlier, I'm Lou Panico, CEO of XENON Corporation. So, what is XENON? In 1963, our company was formed, and it happened to be the same year that a ruby laser was developed for scientific research. It was called a ruby laser because it contained a ruby crystal, and that ruby crystal required incoherent light and a huge amount of photons. The problem was the ruby crystal could only accept light for 1/10,000th of a second to 1,000th of a second. So the beginning adventure was how to get a huge amount of photons into a very, very short period of time. And these lasers at the time were actually used for extensive research, and one such program was Dr. Samuel Fine at Northeastern University. And Dr. Samuel Fine was a pioneer of laser eye surgery. So that's where we began, how to generate lots of photons fast by designing and developing new types of lamp technology. So what does the universe allow us in terms of light? Continuous light, like the sun, delivers low intensity levels at relatively long periods of time. For example, delivering in 60 seconds what a single pulse can do in 1,000th of a second. Now, the lightning bolt is more akin to pulsed light. It delivers a very high energy pulse in extremely short periods of time. So pulse light can deliver peak powers up to 100,000 times higher than the sun's intensity on the surface of the Earth. The sun's intensity is 125 milliwatts per square centimeter on the surface of the Earth. So what we do, we design and develop and manufacture high-performance pulse lamps and related electro-optical systems as illustrated in these photos. How we do it? For over 50 years, XENON has perfected its expertise to enhance pulse light technology in its applications. Our unique systems combine proprietary lamp technology, proprietary gas mixtures, customizable high-speed electro-optical components, as illustrated here. That lamp up in the right-hand corner looks like the grill of an electric stove, but if you ever purchase a Blu-ray disc, it was made with that lamp. So why we do what we do? We do what we do to change the way light is used for the good of all by constantly challenging the status quo. For example, disarming the repair mechanism of a DNA so the cell can be completely destroyed, extending shelf life of food without chemicals, and enhancing mushrooms with vitamin D with a single pulse of light in 1,000th of a second, so fast that there's no possibility of thermal buildup. Pulse light and food production. XENON's pulse light technology is a fast, chemical-free process delivering pathogen reduction for applications including food sanitization and enhancement, food packaging, shelf life extension, and continuous online conveyor treatment. This webinar will include continuous conveyor treatment in the food production process. XENON pioneered this process in partnership with Pennsylvania State University and Cornell University's food technology programs. Pulse light reaches multiple aspects of food production: the food itself, contact surfaces, shelf life extension, and enhancement with vitamin D, as I mentioned earlier. On equipment, as of this webinar, anytime conveyor treatment. Packaging, online sanitization sheet, continuous running and finished packages, floor protection, shoe sanitization at food production plants, and area, space, and air treatment with robotic and/or fixed position pulse light systems. This illustrates our Z2000 conveyor treatment system. It is food grade, controllable, and lamp housing, designed to meet IP67 and NEMA 4x standards, and additional white papers on the right-hand side. That's the Z2000. Now here we have the chemically free dry zap system developed and manufactured by CleanBeam. Pulse light effectively eliminates harmful bacteria and other viruses to sanitize footwear between sterilized and uncontrolled environments, ensuring food remains safe and people stay healthy. And we can see that white section there is a representative of a booth about to step into the machine to be treated with light instead of chemicals. And we've all seen a food production plant with the chemical baths for shoes. Sometimes there's up to 3 baths that you have to step in to get okay to go into the plant. Well, one thing you notice is there's liquid on the floor. And that liquid, of course, is an attraction for listeria, hence the motivation to develop the dry zap by CleanBeam. What about combating COVID-19? XENON's pulse lamps are at the heart of a revolutionary product being used for space sanitization in hospital rooms, airports, trains, and more. Currently, there are more than 2,100 systems in use worldwide at over 600 hospitals. A single unit kills bacteria and viruses on exposed surfaces in approximately 5 minutes. This replaces the use of many hazardous chemicals and/or use of traditional UV lamps, which contain mercury and take up to 5 to 10 times longer. We truly see with pulse light a ray of hope during the COVID-19 crisis. I would now like to hand this over to Dr. Saad.
Thank you. Hello, everybody. My name is Dr. Saad Ahmed. I'm the VP of Operations here at XENON. Today I'll just basically be introducing the technology of pulse light, what it is, and lay it out in very, very simple, basic terms. I will sort of go into why the technology is pertinent and useful for specifically for food, and in terms of its germicidal effectiveness. I will conclude with some case examples of deployment for the system. So if we start by saying, yeah, we have a light source at XENON Corporation, and this is what we refer to as the XENON pulse lamp. And just to bear a comparison between the XENON pulse source and other common light sources, such as a light bulb or a mercury lamp, we see that typically the energy that we deliver with our lamps is 1,000 watts as opposed to 100 watts. And so that's an order of magnitude more energy that we work with. We use a gas discharge mechanism to generate our light. A light bulb would use a filament, and a mercury lamp would have mercury vapor excitation. Again, the differences in terms of, you typically drive your light bulb with mains. We need to drive ours with a high voltage supply. Our light sources are very, very broad spectrum. That means they cover the deep UV all the way up to the infrared. The mercury lamps predominantly only deliver UV. Our lamps are instantaneous in operation. That means they turn on and off when you need to turn them on. Other lamps require times to build up or turn themselves on. Our lamp is made of something inert. The mercury lamp, for example, contains mercury, which obviously is not a safe thing to do. Our technology is based on pulsed light, whereas the other systems are continuous. What is the advantage of the pulsed light, and what is the feature of this pulsed light is sort of illustrated here. If I had a 100-watt bulb, I can quite easily compare it with a 1,000-watt source by saying that's equivalent to 10 bulbs. So you see my blue rectangle around 10 bulbs. That's about the equivalent in terms of brightness of our light compared to a standard light bulb. But if you take that continuous energy which we are delivering, and if it was, let's say, 1 watt as an example, we would say that it's delivering 1 joule of second as a continuous source. If you were then to take that same energy and do it in half the time, you would be delivering 2 joules of energy in half a second, which is exactly the same amount of power, 1 watt. And if you then compress it even more, you could bring it down to 1 millisecond and have 1,000 joules of energy, and that's still 1 watt. So in terms of brightness, you could compare our light source in terms of brightness to be 1,000 times the 10 lamp system that we have, so 10,000 bulbs worth of intensity. But don't forget, this is happening over a very, very short period of time. And this energy delivery over a short time is, this high energy delivery over a short time is what makes the system very, very effective at killing and doing damage to cells. So it's much more akin to trying to use a hammer to bring down a nail rather than using your thumb. And you can, in both cases, you could be delivering the same amount of total energy, but because you're hitting it very, very hard and very, very short, you can get a lot more effect. Again, we talk about the broad spectrum light. Our light sources, here's a typical spectrum of our source, which goes deep into the UV, around the 200 nanometers. The visible part of the spectrum is rich as well, and we have plenty in the infrared as well. So all parts of the spectrum are very, very useful for in terms of being effective at killing microorganisms. The UV part of the spectrum can be divided into 3 categories: UVC, UVB, and UVA. Our lamps have can have filters on the envelope itself to cut out different parts of the spectrum so that we can generate sort of less UVC and more UVB if you want, or less UVC and UVB and get more UVA. The reason why you would want to do that is that if you have a lot of UVC generated, as with our lamps, you do generate ozone, and you would want, in some cases, to mitigate ozone and yet remain germicidal. So so we can have different kinds of envelopes where we have different kind of spectral output from our lamps. So the xenon is a cool technology. Reason we refer to this as cool is because even though we're delivering intense pulses, you know, there is a lot of time between the pulse being on to when it's when it's off, and this high energy is good at killing bugs, but because the duration between the on time and the off time is so long, it does not increase the temperature of your produce. And that is very, very important if you were to deal with produce which is already frozen or just coming out of the freezer. Then you'd want to make sure that you're not elevating the temperature too much. The features of the cooling is really akin to you trying to touch a hot plate. So if you had a hot plate and you had your finger, it could be really, really hot, but if you just touch it really quickly, it doesn't do any damage to your finger. And it's exactly the same kind of thing that we're talking about when we're dealing with pulse light. So now we're going to talk a little bit about actual microorganisms and why the pulse light is effective. So when we look at our broad spectrum light, which covers UV and the visible and the infrared, we find that different kinds of organisms are more susceptible to different parts of that spectrum. And because we deliver a broad spectrum source, we can actually have a much more wider coverage in the kinds of pathogens and much more effective at killing a broad spectrum of microorganisms with it. This illustration is just more of an illustration than actual hard and fast boundary between the different regions of effectiveness. Another important thing to consider is that because we use broad spectrum source, the spectrum of light is capable of interacting with the cells in different ways. And we refer to this as a multi-pathway extinction process. This is saying that, yes, the UVC, which we know is capable of damaging the DNA itself, is very, very useful in terms of being germicidal. But there's also UVB contributions to this thing. There's visible and infrared contribution to this thing. Blue light and all the different parts of the spectrum impact the cells in different ways. And because we are delivering such an intense amount of photons in these ranges of spectrum, we are able to have significant impact on the organism itself. One thing to bear in mind is that cells are used to the idea of being bombarded with UV, and they have a self-repair mechanism, and that self-repair mechanism is called enzymatic photoreactivation, and that illustration on the right is showing how the DNA repairs itself in time. And what we are saying is that with our pulse light system, we are able to do so much damage to everything from the cells and the proteins engaged that their repair mechanism is effectively neutered. Now let's look at the pulse light in terms of deployment in the food industry. We can look at it in terms of raw produce going in to a production process, some production machinery, which is doing the processing of the food, and then some packaging process, and then some shipping process, and then heading off to the customer. Now, at various stages of this process, we can have a pulse light providing effective solutions. The typical standard solutions which we have is with raw produce, we may have a cleaning process, a wash down, maybe some chemical cleaning may be done on the raw produce itself. In the production machinery, we may have a regimen of periodic cleaning, hose downs, And when we go to packaging, we have sample testing and things like that. Where we come in is that we can say that for the raw produce, we can treat the raw produce itself and help to enhance the shelf life of raw produce. We can treat the conveyor or the transport mechanisms which are part of the production machinery, and we can do that dynamically while the system is in operation without requiring the system to be shut down. And after the packaging, we can also treat the produce from outside the package and provide some form of terminal sterilization, which is through package treatment. An interesting thing is that with the advent of COVID, the requirements now seem like they're leaning towards people interested in sort of sterilizing or cleaning the containers, the shipping containers, which or the transport vehicles which transport the goods. So that's a basic overview of the process, and we can say that we want to use our pulse light to replace some of the existing cleaning and treatment steps, or we can use this as a hurdle process where it's another hurdle for the microorganisms to overcome in terms of having different processes to try and reduce the bioburden. Okay, so shelf life extension of blueberries is a good example of how we use pulse light for treatment of the raw produce itself. Now, blueberries are interesting in the sense that they have a white bloom on the surface of the blueberry, and this bloom is very, very sensitive to any form of cleaning kind of process. So apart from maybe just a water bath, there's very little you can do in terms of treating the blueberries prior to the existence of pulse light. So what we have in our system is a case where we can control the amount of energy that we deliver onto the blueberries so that we can maximize the kill but preserve a lot more of the bloom. And that preservation of bloom becomes an added protection mechanism for the blueberries, and we've deployed this method quite successfully. One interesting thing to note is that when you're dealing with three-dimensional objects like berries or produce, that you have to figure out how to maximize the lighting from various angles so that you can get more exposure and less shadowing effects. Conveyor treatment is a very, very interesting position for XENON Corporation. Typically, when you look at a conveyor process, what happens is that a conveyor is continuously going around, food is being deposited on the conveyor and it's transporting it over. The food itself has some bioload which it has collected, and over time that belt builds up that bioload, and that's what requires you to stop the process, clean everything down. And what we propose is that the use of a pulse light to be continuously treating that conveyor would gradually bring that bioburden down. And you see my little bar chart down there that every revolution of this conveyor through the pulse light system is bringing down that bioload. The red is what gets subsequently added every time new produce is rolling on top. So, but ultimately, this graph over time brings the amount of bio burden on that conveyor down to mitigate you having to have a full stop and wash down cycle. You could take that wash down cycle and make it more happen over a longer period, so that you can get more produce through your system. Another thing is pulse light in terminal sterilization. And what the idea behind this is that once the food has been packaged, you can create films and coverings on your packaging, which will be UV transmissive, and they will transmit the UV and kill the pathogens inside your package, at least on the outer surfaces of that package, as we go along. So to the right, there is a chamber example which has a light source on the top and a chamber where you can put packaging through, and you can quite easily imagine this to be a tunnel-like approach. We also offer a wide range of R&D solutions for people who are interested in using pulse light or to develop processes based on that. And the reason why it's so important is that we have a lot of different variables to play with. You can change the width of the individual pulses, you can change the amplitude of the pulse, the frequency, the number of pulses, the total energy, and by being given that flexibility, you can optimize your process so you can have the most effective energy delivery to get you the best kill without compromising on on the actual features of your produce itself. So I think it is very, very useful to have these tools to actually do these kinds of testing. And we also at our facility have an application lab where we do a lot of microbiology testing ourselves. So with that, I'll finish with the discussion about the container storage. And just thanks to COVID, the requirements are that people are saying, oh, we don't want to, we're concerned about shipping produce from one sort of high contaminated area to country to another one. Is there ways of us doing quick treatment of these kinds of containers? And we've been getting requests for that. And so I'm just illustrating that we as manufacturers of pulse light equipment and systems, we can make lamps and systems which can be tailored with all sorts of dimensions in mind. We obviously understand that the food industry requires a fair degree of customization as well, and we are suited to that kind of environment. The example I'm showing here is that we've got a 60-inch lamp which was designed to have a very, very uniform footprint, but we are not restricted by any kind of dimensions or geometries because we manufactured the lamp, the electronic systems, and all the control mechanisms that are associated with that process. So with that, I'll send it over to Beining, our microbiologist, to tell you a little bit more about the biologic aspects of our technology. Thank you.
Okay, thank you, Dr. Saad. Hello, everyone. My name is Beining Ouyang, and I'm a microbiologist in XENON Corporation. And here at XENON, I do microbiological testing with pulse light And also I do germicidal insecticide testing using pulse light on all kinds of applications. So in this part of presentation, I will talk about a brief introduction about pulse light, and I will talk about the mechanism of pulse light on bacteria, how does pulse light kill bacteria, and also the applications. And then I will present some log reduction data from literatures and also some scientific research we did here at XENON. Okay, let's start from pulse light spectrum. So Dr. Sad already talked about a lot of fundamental details about pulse light. Here, I just give a quick introduction. So we all familiar with UV light. UV light is the spectrum is from 100 nanometer to 400 nanometer. However, pulse light is much more than that. It's from 100 to all the way to over 1,000 nanometer. It is broadband spectrum. So it's not only including the UV region, but also the visible light and even the near infrared. So this broadband spectrum enable pulse light deliver massive peak power, very strong power in very short period of time. So it's very efficiency in killing bacteria. So how does pulse light kill bacteria? There are three mechanisms. The first is called photochemical, which means the UV wavelength, UV region, can get damage on DNA and inhibit the replication of DNA. Although cells do have the repair mechanism, but like Dr. Saab said, this power is so strong and high peak power, and it overcomes the cell repair mechanism. So the cells are not able to recover and finally death. The second mechanism is thermal shock. So this broadband spectrum can generate localized heating at the cellular membrane. And this happens instantaneously, so it won't increase the overall temperature of the whole thing, but at a micro level, it contributes to the damage of the cell. The third mechanism is physical effect. This strong pulses can generate micro vibrations on the cell, which lead to the cell rupture and cellular content leakage. The picture on the right shows a cell rupture and cellular content leakage after exposed to the pulse light. So the germicidal effect of pulse light can be applied to a lot of places. For example, air sanitization, you can use it to clean room, clean hospital. We actually have thousands of units doing right now. And to clean hotel, office, you can also install the whole unit in the dynamic air system to clean the air dynamically. And for food industry, it's very effective in clean surface or food packaging materials, including but not limited to metals, stainless steel, or plastics, or kind of material of cutting boards, trees, etc. So we designed all kinds of products for different needs and different applications. The picture on the left shows the modular system, RC800 and 900. These units are designed for manufacturing, and you can install the units in the processing line to treat the product, and also you can install it with the air system, etc. And picture in the middle shows a conveyor decontamination system, and this product is designed for the conveyor system. You can use the Z2000 to sanitize the conveyor and also the product on the conveyor. The picture on the right shows a research system X1100, and this unit can be used in lab and for characterization or optimization. This unit, you can change all the treatment parameters like different voltage, distance, or pulse rate, or energy per pulse, and more to optimize the maximum germicidal infection and get the desired log reduction. And this slide shows the log reduction data I got from some literatures. So here at XENON, we have great relationships with universities. We do fundamental research and also application studies with universities like Penn State, University of Florida, Cornell, and there are tons of papers published have been proved that xenon pulse light can kill common pathogens like Staphylococcus aureus, E. coli, Salmonella, Listeria, and more. So here I only list 3 examples. The first one is an example in hospital. So this paper used the xenon pulse light to treat the high touching surface, and after pulse light, the Staphylococcus aureus abundance was decreased by 72% compared with manual cleaning. And second row is example on food. It's an application on food surface, and this paper used sterile pulse on the cheese surface, and we got 3 log reduction after pulse light of Listeria. The third example is a fundamental research on liquid media. And after 12 to 14 pulses, we got minimum 4 log reduction of E. coli. This is just about 5 seconds for 12 pulses, which shows pulse light can kill the pathogens very quickly and efficiently. This slide shows some scientific research data I did at XENON, some log reduction data on hard surface. So for this study, I used the X1100, the research system, to kill E. coli on aluminum foil. So you can see we have all different parameters. We can change voltage, the energy, and we can change the distance, and we can control the pulse numbers. And you can see in the log reduction row, the minimum log reduction we got after 1 pulse is higher than 2 log reduction, which is very impressive. So other than germicidal effect of pulse light can also be used for food enhancement. For example, it can be used to enhance the vitamin D in mushroom. So argosterol, which is rich in mushroom, it's a pro-vitamin D. It can be converted to vitamin D2 by UV light, pulse light, or sunlight. However, for the traditional UV light or sunlight, it's a quite slow process. But pulse light can turn this process very quickly, just in few seconds. This table shows a study done at Penn State. And they used the sterile pulse to treat mushroom, and we can see in first line, they did on fresh bottom mushrooms, and after 3 pulses, which is 1 second, vitamin D was increased over 100% daily value. And second line shows on oyster mushrooms. After 3 pulses, is still 1 second. the vitamin D to increase from 15% daily value to over 1,000%. And third row shows shiitake mushrooms. After 1 pulse, vitamin D increased to 490% daily value, which is very quick. So finally, COVID-19, the topic everyone is concerned now. And here at XENON, we have a solution for it. So pulse-like can kill COVID-19 virus. This paper was published just 2 or 3 months ago, and it shows with using XENON flash lamp within 1 to 5 minutes, we can efficiently kill COVID-19 virus on both hard surface or masks. And here is our combating COVID-19 with pulse light video.
And that solution was there all along, right in front of our eyes. For centuries, we've known about UV light's ability to destroy pathogens. And for decades, XENON Corporation has been harnessing the power of pulsed light to disinfect and decontaminate surfaces in laboratories, hospitals, and food processing plants.
Thank you so much. So this is the end of my presentation. And we prepared all the resource and information for you. Can we complete our brief survey, and then you can get all the document, application sheet and papers and more. Thank you so much for listening, much appreciated. And you can reach out in the following information. Our email is marketing@xenoncorp.com. You can also find us in LinkedIn, Facebook, Twitter, and YouTube.